This is the example on slide 47 of our chapter 21 PowerPoint, and here we're going to be solving a problem using radioactive decay kinetics. So we've already technically learned both of the equations we're going to use back in our kinetics chapter, but here we're going to be using it in the context of basically nuclear decay. So instead of concentrations, in this particular problem, we'll be dealing with mass amounts. So the question says, plutonium-236 is an alpha emitter with a half-life of 2.86 years. The sample initially contains 1.35 milligrams of plutonium-236. What mass of plutonium-236 is present after 5 years? So our strategy for solving this is twofold. First, we're going to use the half-life equation for nuclear decay to determine our K, which is our rate constant. And then we're going to plug the values that we know into the integrated rate law for nuclear decay. So I have the two equations we're going to be using written here. Hopefully they look slightly familiar to you. This first one, that's our half-life equation. Half-life is equal to 0.693 over K. And this happens to be the half-life equations for a first-order type of reaction, but pretty much all radioactive decay undergoes first-order kinetics. And then our second equation, that is the integrated rate law for a first-order type reaction, which nuclear decay is. And it's the natural log of N sub T, that's the amount of radioactive nuclei at a given time. In this case, we're going to be using amount in milligrams. And then over N subscript O, which is basically the initial amount of our radioactive nuclei that we have. And that's equal to negative K, rate constant, times T, and that's our time. So in this, we are looking for NT. How much is left after a particular amount of time, which happens to be 5 years. So some things that they gave us in this problem, they tell us that our half-life is 2.86 years, and they tell us that we're looking for the amount of something after 5 years, and that our initial amount, N0, is 1.35 milligrams. So we have these three values, and what we're looking for is NT. And we also, before we can plug these values into our first order integrated rate law, we have to figure out what our K is. So that's our first pit stop. So T1/2, our half-life, is 2.86 years, equal to 0.693 over K. So I'm going to multiply both sides by K to get it out of the denominator. And then I'm going to divide both sides by 2.86 years. So K is equal to 0.693 over 2.86 years, which should give us a rate constant of 0.24231 over years, or inverse years, however you like to write it. So now that we have our K, we can begin to solve basically our integrated rate law equation for this amount at the specified time. So before I start plugging numbers into this equation, I want to get N sub T the amount at a certain time isolated by itself. So to get rid of a natural log, remember we take e to that power. So that cancels out our log. Whenever we do to one side, we do the other. So it becomes nt over n0 is equal to e to the negative kt. And then we can multiply both sides by n subscript o to get nt completely isolated. So n sub t is equal to e raised to the negative, oh, hold on, let me rewrite that. N sub o times e to the negative kt. So if we plug all our values in, our initial concentration or amount is 1.35 milligrams, and e is raised to the negative k. K is 0.2423 inverse year. That comes from this right here, which we solved. And then our t is 5 years. So notice here I'm leaving my time in years because my half-life was in years, so there's no point in changing units. In our previous chapter, a lot of the work we did was in seconds, so we had to deal with that. But here, years is fine. So notice that year and inverse year cancel, so that's going to be left unitless. And now we can multiply everything out. 1.3 milligrams times e to the negative 0.2423 times 5. And we get that the amount at our specified time is 0.402 milligrams. So our concentration or our amount of radioactive nuclei after 5 years is equal to 0.402 milligrams. And that is your final answer.